Hi, we are Team 5 from BMSCVT Neuro Lab and Genomic Medicine Lab. Our project title is Enabling Cultivated Meat as a New Protein Source by Mass Production via Serum-Free Culture Medium and Novel Bioreactor Platform. This project asks a simple question with a complex answer. Can we grow real meat from animal cells by the ton at a price people can actually afford? We'll argue this is fundamentally a biomedical engineering problem and will propose one integrated platform to solve it. What is cultivated meat? Cultivated meat, also called as laboratory meat or in vitro meat, refers to meat produced by artificially growing animal muscle and adipose cells in a laboratory environment. By using cell culture technology instead of traditional livestock farming, it produces meat with a texture, flavor, and nutritional profile similar to real meat. This process eliminates the need to raise or slaughter animals, holding great potential to significantly reduce environmental impact while addressing animal welfare and food safety issues. So, how is cultivated meat produced? Edible microcarrier derived microtissues are first produced in a scalable bioreactor and then undergo processing approaches such as aggregation or homogenization. Then the processed cellular mass is further incorporated with an oleogel-based fat substitute, followed by food processing methodologies to the same prototypes. Some people may be reluctant to eat this type of meat considering it is made artificially. However, the science has already proven. The first products got permission for sale in the US in 2023, but the industry still faces major challenges like high cost and mass production. So the question is no longer can we make it? The real bottleneck is this. We can make it, but not yet cheaply, nor reproducible, nor at the scale of a food product. Our proposal attacks that bottleneck by engineering two things together: a serum-free growth medium and a gentle sensor-controlled bioreactor built around an engineered growth surface. To see why this is challenging, look at what's been tried so far. On the medium side, early work depended on FBS. It worked, but it's expensive and animal derived, and it defeats the whole point of reducing reliance on livestock. The good news is that serum-free media recipes now do exist. Kaplan's group built one called Biffy9, and Musacio's group made chemically defined media for bovine cells. So serum-free medium is feasible, but it isn't affordable. On the engineering side, the surface matters as much as the food. The muscle stem cells on stiff plastic quickly lose their ability to keep dividing, while on a soft surface, they keep renewing. So the surface is an active biomaterial that instructs the cell. Second, these cells are fragile. Stirring too hard and the tiny turbulent eddies literally tear them apart. Therefore, it's important to design an environment where cells grow densely without being destroyed. According to FAO and OECD, global meat consumption and production is projected to keep growing for decades. Cultivated meat could ease pressure on land, water, antibiotics, and animal slaughter. But those benefits are not automatic. Life cycle studies show the environmental payoff depends heavily on the energy source, the medium formulation, and how efficient the process is. The benefits are an engineering outcome, not a guarantee. So the urgent question is, can we build a process that is serum-free, scalable, cost-efficient, and genuinely compatible with food production? This leads to our main goal, which is developing an integrated serum-free culture and bioreactor platform for mass-producing cultivated meat cells. Our central hypothesis ties those pieces together. If we co-optimize three things, one, a cost-reduced serum-free medium, two, edible or degradable microcarrier, whose surface chemistry and stiffness are engineered for muscle cells, and three, low-shear sensor-controlled bioreactor operation, then we can expand these cells at scale, keep their muscle-forming ability, and do it at a lower cost per unit of biomass. Our approach is built on one core principle, optimizing the cell, the medium, and the microcarrier and the reactor as a single coupled system. A medium that works in a still dish can fail in a stirred tank. Mixing faster improves oxygen and nutrient transport, but it also raises cell death. That's a direct engineering trade-off. So we follow a three-stage workflow as shown here. This would match every techno-economic analysis.
Then we break that into three specific aims: a cost-aware serum-free medium, and an engineered growth surface and a gentle reactor, and developing self-correcting systems. Aim 1 is about developing the medium. We start from published serum-free recipes like BF9, then screen to cut the expensive ingredient like albumin, transferrin, or insulin. We're also redesigning growth factors so they last longer in the tank and cells to make their own signals. And we measure whether they stay muscle with markers like PAX7 or MyoD. Then we track cost per gram. Aim to design the surface and the reactor together. A microcarrier is just a tiny bit cell grows on, but we treat it as an engineered niche and tune three properties. First, we cut surface with cell adhesion anchors like laminin, which improve attachment and purity. Second, we'll match stiffness to muscle, so cell keeps self-renewing instead of differentiating too early. Last, design carriers that can either stay in the final food or be removed cleanly. And then before scaling, we use AI to predict shear and oxygen transfer. AM3 turns the reactor into a self-correcting system. We add inline sensor for glucose, lactate, oxygen, pH, and live cell mass, and close the feedback loop so feeding and conditions hold themselves at target automatically. We identify the process parameters that drive quality and build a simple digital twin to guide scale-up and medium recycling. This is where cost gets solved in practice. Recycle medium, retain the expensive ingredients, remove waste. The proposal is not complete without the honest risk and backup plans. If growth is too slow in serum-free medium, we withdraw serum stepwise, adapt the cell line, or use engineered autocrine signaling. If cells lose their muscle potential, we split the process into a growth phase and maturation phase. Then keep the substrate muscle soft to protect stemness. If shear damages cells, we lower the impeller speed or switch to gentler reactor formats guided by computational fluid dynamics. If cost stays still high, we attack several cost drivers at once and recycle medium. If tissue lacks texture, we add edible scaffold. And if sensor drift or foul over long run, we use redundant probes and software, the soft sensors that estimate hard to measure variables for reliable ones. If this works, it delivers three things: serum-free culture method, engineered biomaterial, sensor-controlled bioreactor platform for mass production, and a cost-aware process model that links biology to industrial feasibility. The bigger picture is cultivated meat moves from a demonstration to manufacturable protein sources. We claim that it becomes one part of a diversified protein system, especially where land, water, and disease make conventional livestock harder. And we hope that our toolkit can be transferred directly to regenerative medicine and cell therapy manufacturing, which face the exact same scale-up problems. Thank you for listening our presentation.